Eventual consistency. This is a term that you're going to hear quite a bit in this space. So it means that all replicas of your data will be the same eventually, right? It's kind of a little bit of a scary term. We don't want our data to be consistent eventually. We want it to be consistent right now. But eventually could be in the order of milliseconds, could be seconds, it could, depending on how large the cluster is, how many copies, and so on and so forth. So not all applications are necessarily compatible with eventual consistency. So if you're doing, if you're doing stock orders, when you place your order for your stock, you don't want eventual consistency. You want hard consistency, and you want it right now. However, we all know with our checkbooks, writing checks is always eventually consistent. If I write a check and I give it to Walmart or whatever, eventually it will make it through the bank and into my account, and it will get updated, right? That's eventual consistency. But that's, of course, on the order of days or maybe weeks sometimes, depending. And there's a few different ways that some of these products use to ensure that your data is consistent. Vector clocks, which basically can tell when different pieces of information are written or read, right? So we know this happened first and then this happened after that. Read repair has to do with, so if I read 3 copies of the data, but 2 of them agree and one copy does not agree, when I read that information, then some data stores will say, okay, well I have 2 that are good, and I have 1, I think this one's bad, so I'm going to update that copy and return the information, right? And gossiping is a technique where different nodes in the cluster will create hashes of the information they have and pass them to other nodes and say, well, this is the information I have, is this the information that you have? And if they agree, we know that the information is good. If not, then they can trade information to keep that up to date. The other way to go is where the data store will simply punt and give the information to the application and say, hey, I got 3 copies, you tell me what's the best copy. You're the smartest one in this case, right? So a little bit of SQL and NoSQL comparison here. So on your left-hand side is kind of the SQL style RDBMS. On the right is more the NoSQL style. So in the RDBMS world, the products tend to be more vertically scalable, which means if you run out of horsepower on your database, you get a bigger box, right? The NoSQL world tended to come out of more of a horizontally scalable, where I don't care if my individual box works well or not, I'm just going to get a whole bunch of them. And the idea is not only can we tolerate that things will break, hardware will break, but we're going to even make the assumption that things are going to break all the time. If you consider a cluster, if you have 1,000 nodes, and if each node has 4 hard drives, you've got 4,000 hard drives, 1,000 nodes, you've got something breaking every day. So how does the software actually, your data in particular, how does it tolerate that and not only work in that environment, but work very well and anticipate all that and work like that, right? I talked a little bit about some of the cap scalability. Partitioning is basically part of the equation in NoSQL. In NoSQL Land, I mean, it's not impossible. I mean, all your RDBMSs will scale. It's just a different proposition, and it's not necessarily, it's not what they were really designed from the ground up for, right? Of course, in SQL, we have query by SQL, we have our SQL language, we all know that pretty well, I'm sure. A lot of times in SQL land, we're going to have, or sorry, not SQL land, NoSQL land, you're going to be dealing with some kind of a custom API or maybe an SQL style language, or sometimes something like SQL doesn't even really apply to that kind of a data store depending. So this makes it more expensive for a company to be able to integrate because it's you're working with custom APIs instead of JDBC or JPA or different things like that. They're really kind of with SQL queries, we're taking information from the data store, right, and we move it to our application and we process it. The kind of the opposite approach is a stored procedure where you take your algorithm and you store it in the database and you run it there. So the equivalent to that in the NoSQL world is called a map reduce. So it's basically a technique where you can take an algorithm, you've got 1,000 nodes, you can run this algorithm across all 1,000 nodes in parallel, and then reduce or aggregate those results into some particular answer. Asset transactions on the SQL side, we have more base style transactions. A number of the products actually do support either full asset or at least partial asset support, and that's where this kind of comes into your business needs. A lot of times in the SQL, we have really advanced indexing support. There's a lot of different things we can do with foreign keys, locking support. We have our schemas, all these things that we love and know. A lot of times on the NoSQL side, those things don't necessarily exist or don't necessarily apply. APIs and a lot of stuff that we're familiar with, and access control. SQL databases, you got to have all your logins, all your access control and stuff. Most of the NoSQL stores, it's not out there, so you don't want to put it anywhere where anybody can get access to it. So you're going to be putting it through some kind of a proxy in front of it, or some kind of firewall, or different things like this to be able to control access. And then SQL has generally very complex on-disk representations. Like, for example, at Oracle, it would actually prefer if you just gave it a bunch of raw disks and it handled everything. It doesn't necessarily want to deal with the operating system. And they've tuned it very well to do all these different kind of random disk access and all these things, so it can really interact with that disk in the most efficient manner possible. On the NoSQL side, usually most of them will punt on this and just say, we're going to completely simplify this model. We're not going to do random access. We're going to do append-only kinds of modes. And then maybe we'll go back and gather up all the results later and kind of compress all that. And when you're reading, usually it knows on disk where that information, so I'll have an index in memory. It knows where that piece of information is physically located. It'll issue a single seek, do a single read, and you're done. You're in, you're out of there. Again, on the programming side, GPA, Hibernate, SQL, a lot of that stuff we know, a lot of multi-platform support. These transactional databases are very good for general purpose things that we do. A lot of very strong commercial support. Of course, you got to pay for it. And tool support is, whatever database you want, there's lots and lots and lots of tools that you can use. So, NoSQL, it's going to put more work on the application dev. That sucks. But, that's not necessarily a bad thing. It just depends on the philosophy. So, for example, with Google's big data project they specifically said, when we design this thing, we're going to take some of the intelligence out of the data store. So we're going to put that specifically on the application developer so they can better tune how the application is interacting with the data store. A lot of times in SQL, you write your queries, and then you run it, it doesn't work well, and then you got to figure out, okay, well, what is the database trying to do with my query here, and how can I better speak the SQL language so I can get the database to react the way I want it to, use my indexes or whatever. A lot of the products tend to favor more of a Linux Unix world. They tend to be more specialized, like especially for GraphStore. GraphStore is really, really super good at what it does, but it's not a general purpose database. So it's not. Commercial support, it depends. It'll go from strong to kind of none. And then tool support, generally not a whole lot. So a little detail here. So with the column stores, this is a little bit of a description of what they are kind of underneath and why they're a little bit different. So with an RDBMS, it basically, I call it a row store. When you write your row of information, it will take and physically store all that information together on the disk in that row format. Which makes it very good for transactions because we're generally updating rows of information, right? So it knows where that row is, it's all together, can update that very quickly.